So today we'll cover the contents of week 7, which is focused on torsion. And sir has taught 3 videos. Like there are 3 video lectures on torsion taught by Professor K. Ramesh. So I'll cover the first 2 of them, and Archita, who is the second TA, will cover the third one. So the first two will be concerned with majorly understanding torsion, what is the stress state in torsion, and how you can mathematically represent it. And the third one is related to problem solving. So applying the concepts and relations for real world applications. So for example, shafts and gears, for that. So okay, let's start with the summarization. Quickly, we'll look at the major points which sir covered in his lectures. Mm. S- Krishnakant, you could go through the video lectures for this week if you have gone through them.
Almost done, sir.
Okay.
First and second are done. Third lecture is only 10 minutes pending.
Hmm. Okay, that's good. Mm. Ah. Mm. I think today also the discussion will be majorly between the two of us. So let's start with what were the some of the concepts which you covered, and you let me know what doubts you have or anything you want to discuss more with me on. So, in the rest of the course, we'll majorly be focusing on torsion and bending. I think a uh, lots of lectures are there on bending. In this week, torsion got over. So torsion. So what we are trying to study is how a shaft resists torsion, what are the stresses that develop and the resulting strains that develop in a shaft, because shafts are very commonly used in everyday engineering applications for transmission of power. And later on we'll look at bending of beams, which is also just as pervasive in all applications. So, sir has mentioned multiple times when teaching this that we are going to make a assumption while building up all the key concepts and making derivations, and that assumption is that all the members, may it be the shaft for torsion or the beam for bending, they are all slender members, which means that the cross section is very less compared to the length of it. And then we can understand what is the power that is generated when you are applying a torsional load, or the power involved with a torsional load, and that can be represented as the torque into the angular velocity. Just like you have force into velocity in other cases, like rectilinear cases, here we have torque into angular velocity. And then when we looked at cylindrical shafts, because that's the most simplest case, so we started looking with cylindrical and slender shafts. And there sir showed that each cross section will transmit the same twisting movement in a shaft. Um, so one way to understand this is that if you have a shaft and you are applying a twisting kind of load on it, so maybe one end is fixed and the other end is being twisted, then at any cross section, the if you look at what are the stresses and what is the movement that is acting on that cross section, it will be exactly the same. Then if we are assuming axial symmetry, then in that case all the lines of deformation will lie on the same plane. So this is also, maybe I can just write it as uh, some points which tell about how the deformation is if you are having torsion. So for axial symmetry, all the lines of deformation, um, you can understand it as if you had a hypothetical line in undeformed material, undeformed shaft, and then you deform it, then how will that line change on deformation? So here it is said that it will lie on the same plane as it was earlier on. Then another aspect of it is that by using some sir called it thought experiments. So by using some thought experiments and considering the symmetry of the shaft, it could be shown that these lines of deformation will not be curved, they will be straight lines. So if there was a line and it was deformed, it will not curve, it will just move radially, not really radially, it will just move as along the direction of twisting, but it will still remain linear. This is also a very important point. Uh, all this is clear to you, Krishnakant? These are the, I think, major things you should know for understanding torsion and solving problems on torsion. Then if you do not have a cylindrical circular cross section, that is, you do not have the circular symmetry, and if you have some other cross section like a square cross section, then sir told that you can have something called warping. And what happens in this, if you have seen the lectures, you would have known that maybe I can draw it, I can attempt to draw it here. If this is your cross section and this is a square shaft, you twist it like this, then what happens is that the deformed lines, like the deformed lines will not be on the same plane, they will become curved. And this phenomena is called warping. So we told, right, for axial symmetry, we'll have them on the same plane, but in case of square cross section, we won't have that. Also, we established the convention to use to denote the uh, value and sign of the torque or the movement. So the movement will be considered as positive if it is clockwise, sorry, if it is anti-clockwise, it will be considered as positive when you're looking at the face. And when you're looking at the face and it is clockwise, it will be negative. So this is, I think, the general convention with other things also, that anti-clockwise is positive and clockwise is negative. So for example, this particular uh, you can call it, this particular material having this free body diagram has a positive movement because from either face it's on anti-clockwise. Then yeah, we have the cylindrical shaft, and if we look at what will be the shear stresses and strains developed in the shaft, since we have already told that the deformed lines are linear, we can also try to uh, measure the shear strain value. This is, and it comes out to be equal to r d phi by dz. So this varies linearly with radii, and it is uniform for all the sections. So d phi by dz will be a constant value, which will depend on how much torque is applied. Then also the assumption here is that the material is isotropic, and um, the effect of assuming isotropy is that shear stresses only cause shear strains and normal stresses only cause normal strains, and vice versa. Then we can, based on this isotropy assumption, we can calculate this shear stress also, and it is nothing but g into the shear strain value. Also, sir mentioned that the epsilon value, which is going into your strain tensor matrix, will be equal to half of this gamma by 2. Ah. Also, when you have a shaft on the outer surface, you have a free surface. And as we studied in some of the previous lectures, for a free surface, the stress vector on the surface is 0. So on the plane on the surface. So that again we have to keep in mind. And sir did some calculations to find out the moment, because the shear stress is which is shear stress in the material is dependent on the radii of the material, right? Radii of any element that you are considering. So it will vary along the radius linearly, we have seen here. But if you want to find the movement of the load applied, then you will have to integrate it from the center to the surface of the shaft. And when you do that, you will find out that the relation will be something like this. So you will have to use moment of inertia, which incorporates the shape of the shaft, and you will have g into I into d phi by dz equal to m, the moment. And here g into ip can also be considered as the torsional rigidity, because it gives you uh,
Sir, one
some
small,
sense of how rigid your shaft is. You want to say something, Krishnava?
yes, sir, a small doubt here.
Yeah.
We are seeing the moment is as same as how we apply pure shear. So is
Can you repeat?
moment and shear stress. We are
Fine,
seeing
fine.
here as a moment. How we are applying moment is as same as how we are applying pure shear. So is moment and pure shear same? Like moment and shear stress same?
Uh, Movement and shear stress, whether they are same. Mm, no, they are not the same. The direct answer is they are different. I'll try to explain you how you can understand movement. So,
Mathematically, I understood. So stress into
hmm,
area equal to force, force into R equals to moment. But the
hmm.
application consideration has on the surface in a rotating manner.
You are saying application wise, you want to understand.
While applying in the shaft.
Hmm. Uh, okay. I'll have to think a bit. So let's just say, let's just think a bit on how movement can be understood. So if you have this kind of, let's say, cross section, you applied some movement. So you understand if you have a shaft, let's say, mm, maybe here, yeah. So often there is just a force being applied, right?
Hmm.
Some forces are being applied, maybe for transmission of power or some other purpose like this. And due to those forces, there is a torque which will be experienced. And because the radii of this, you can call it a pulley or radii of whatever kind of uh, arrangement you are using, that is also affecting how much, we call it movement only, how much is the movement that is acting on your shaft, because this is the shaft, right? So
Hmm.
here this is the shaft, and you can understand the more the radii is, even if the torque is the same, the farther is the distance at which the torque is applied, the more will be the
Moment.
twisting movement being experienced by the shaft. So you can
Hmm.
understand it as the twisting movement. So how much twisting force is being experienced. So that is what we mean here. And this you have understood, right? What I told.
Hmm.
So one way also to understand this is, hmm, so let's say you have these two different, you can call this a pulley and a shaft, right?
Hmm.
So if you have a pulley like this, then you can calculate some movement which is acting on this setup, right? And this will also act on the shaft, because we know that the same torque, not really the same torque, but the same movement will be occurring based on
Same
free body
force.
diagrams also you can tell, because this is stationary, right?
Hmm.
So same equal amount of movement will be experienced by the shaft also.
Hmm.
And we can also see that, let's say, here you can see the shaft is quite thin compared to the pulley. So from
Hmm.
this we
So
can
torque will
tell
be.
that if the movement is very high, then the forces which are, or stresses which are acting on this thin, slender shaft will be very high, right?
Sir, can you repeat again? That sentence again. If
Hmm.
the force are very high.
So I was saying that if the twisting movement is very high on the shaft, and if the shaft is having a smaller cross section, then the stresses acting on the shaft will also be higher. Maybe by seeing that formula.
Section stress.
So in a way, what I'm trying to say is that, TIP 5 by
Okay, the tau
the,
formula.
huh,
Okay.
how can I say this? let's just consider strain defined by d square. Hmm. So what I'm trying to say, if the twisting moment is high, this is one way of visualizing or having some intuition of movement. That here I'm showing it by formula only. This is how I think of it. That if your movement is high, uh, then this quantity IP into d phi z will also be high, right? And IP tells you about the radii, gives you information of the radii. D phi by dz gives you information of how much strain, in a way, how much strain is being experienced by the cross section, right? So if phi is higher, that means there is more strain being experienced, right? But this will also depend on IP value. So if your cross section is smaller, then the moment of inertia will be also small, right?
Mm.
So correspondingly the strain will be higher because your twisting moment is fixed based on how the loading is. But based on the
Mm.
so twisting moment is fixed based on the loading, and based on the diameter of the shaft or the cross section area of the shaft, your IP will depend on that value. And if the diameter is high, then your IP will be higher, and correspondingly the strain being experienced d phi by dz will be lower. So that way you can have an intuition that a bigger shaft can take more loads because the strains will be smaller correspondingly. So a twisting moment can be just understood as a combination of your torque applied and the geometry or the cross section of your shaft. So
No, twisting moment is torque, right?
twisting moment is
Torque.
not exactly the torque. So torque is more like what is the unit of torque? Do you know?
Newton meter.
Twisting. Yeah, it's Newton meter. Uh, yeah. Actually, you are right. Twisting moment is torque. I was trying to relate it to that pulley and that thing. So, you are right. I was confused.
Like,
So,
sir, if we are taking a 2D cross section
hmm, hmm, hmm.
and we are drawing a torque applied to that object, so we will end up in
Okay.
drawing pure shear.
It will be pure shear. Yes.
Then how to differentiate them in that case? So
Movement
by
and
formula, by
uh,
formula wise, we can mathematically differentiate them. But just by seeing that the cross section, we are getting thought like these two must be same because we are having a same free body diagram.
no, can you repeat the last statement you made?
Like if we see the free body diagram of torque and pure shear. So we are
Hmm.
pure shear stress state. So we will be getting the same free body diagram. So we cannot differentiate both of them just by looking at the free body diagrams. So it is giving an impression like both should be same.
Uh, okay. Pure shear, the stress values
Mhm.
and the torque value in your free body
So
diagram.
the question is, while taking some objects, be circular shaft, if I am applying something, is it a torque or pure shear?
Torque or pure shear?
I can tell. If I'm twisting it like this, can I tell
Hmm.
whether did I apply a torque or did I apply a pure shear force or
So, okay. Maybe I can clarify few things. So, if you have what you just explained, shaft, you are applying a twisting movement. So, it's a torque you applied, right?
Mhm.
Torque is nothing but like in the way we use the term torque, it's some load that is being applied, right? So, applied or being experienced. So you have some torque that is acting on your shaft, right? And mm, now you want to look at the stress state inside your material. So for that, you can take a cross section. You can calculate the, you know, how, what is the torque or the movement, that is twisting movement being experienced. So you can take the cross section. Mm, you know by this that what will be the strains being experienced at different radii, right? Uh,
Trains.
how can I? Okay, so let that be. That comes later. So if you have that material, you have a twisting movement being applied, then there will be some stresses which will be experienced, right? And they will be different at different radii values. This you agree with, right?
Stresses
So
will be different.
and before that, I'll maybe say that the loading, that is the stress state which is being experienced, will be a pure shear one. So that you agree with, because torsion loading is always pure shear. So if you just take a small element in that material, let's say on the surface, then you can just denote what are the stresses acting on it, right? There will be pure shear stresses, and there will not be normal stresses at some particular element. Or you can uh, so what I want to where I am trying to get is that this shear stresses which are being experienced will be different from what you are calling the torque, right? So stress is what is being experienced by some element of the material, and torque is the twisting moment which is being applied. So these are two different things.
Okay.
So did I
Okay.
answer your question?
So
Uh,
we cannot tell like I'm applying a pure shear loading.
it is a pure shear loading, yes.
Okay. Clarify.
Clarified? I'm not sure, but it's understood.
So
Mhm.
yes. Got
So
it.
actually this is new for me also. This I don't usually deal with torsion and those things, because I look at more of the micromechanics related things, not the like bulk loading. Um, So I think this part is understood. Uh, or do you want to discuss this?
That's clear, sir.
So we were around here, not torsional rigidity. Actually, my pen is not
Hmm.
working.
Hmm.
Okay, my pen is not working, but fine. Yeah. So we were discussing torsional rigidity. It gives you some sense of how rigid your material is, and it depends on your moment of inertia of the cross section. And then sir also said that we can consider mt by phi as being a spring constant, uh, and this will be equal to g into ip by the length of the shaft. So the higher this is, the more rigid the shaft will be. Mm, GIPL. Yeah. Hmm. So the higher of GIP by L, the more movement you'll have to apply to cause a particular strain, just like you have in a spring. So that's why this value is being called the spring constant. It tells you how much movement is required for causing a particular amount of strain. So that was all that was taught in this lecture. I think this part is more critical, where sir explains the stresses and strains and derives the value of the movement, the relation between the twisting movement and the this shear stress and strain experienced by the material. Mm.
So just for clarification, we saw in photoelasticity stating that the center part of the beam is not taking part in load. Did we make it in any derivation and proof for that in the till
The okay,
in week 7 lectures?
that the center part of the beam
It's
is
not
not.
taking part in loading. matlab, So in center part there won't be any stress. So in photoelasticity, sir showed that a fringe acid is very
Of a
light
shaft,
in color.
do you mean?
No, on beam, sorry.
The center of a beam. So bending of beam, you mean?
Uh, while
Hmm.
applying load or tensile or compression, center part is not taking part in load.
Yeah, yeah, that is true. Yeah.
Did we make any proof for that or just shown? I actually forgot.
Sir has not proved that yet, but I think we can, and we'll of course look at it when we look at bending in the next week.
Okay.
But here also you can understand it, that one kind of analogy that you can make here is that if you have a shaft and you are applying a twisting movement at the center of the shaft, like the axis of the shaft, you will not have any strains being experienced,
Hmm.
right? So this is also similar to what happens in, no, this is not actually similar. This is something different, I guess, because in bending, what happens is in your cantilever, you will have tension on the top part and compression on the bottom part, and that will also be linear, just like you have here in shaft, which is undergoing torsion. So there also the stresses will be linear, and since you have a positive strain on top, negative on bottom, in between there will be one particular plane which will have zero stresses and strain. So I was just looking here because I got confused when I was explaining you this thing, right? The how the strain varies with radii. So I think this is simple to understand, and stresses can also be understood as G into strain. Then we can integrate it and get the moment, since we know the value of the stress at a particular radii. And what I wanted to, I think, say was that hmm, here this tau z, this is the shear stress at that element, right? This particular element which we are considering, and this is different from the torque which is being applied on the twisting moment, which was applied on your shaft. So those are different, those are different terms having different definitions. We are trying to connect it by using this kind of like by developing these kinds of mathematics. So that's the thing. I think, yeah, that's all in this. Anything else you mm, want to discuss on this?
Just a minute.
Fine, take your time. We have enough time. Just
So in lecture 21,
okay. Mm.
sir says that the loading of the tension spring
Okay.
Is a kind of moment, or we can tell it that
The
torsion like loading.
the loading of a spring, right?
Like, huh. Sir
Yeah.
also said when you apply a load, how it will react. So he said that it should be equal to torsion or rotating moment. Okay.
Mm-hmm. Yeah, yeah, okay. I got your question. I'll go to that part. Uh, so this is there. Yeah, yeah. Hmm. Okay, I got your question. Uh, it's a bit tricky to understand. Actually, sir has told that it will be a pure shear. Actually, it will be a torsion loading. It's even though in this case you have axial loads being applied to a spring. What is being experienced by the spring is actually a torsion movement, like in this part of the spring. Uh, you can read it. Is it?
Yes, sir, I can read it.
Mhm. Mhm. Uh, mhm. So this is all I think. Yeah.
While applying load, how
Uh,
the spring
how
is
it is actually
twisting.
a torsion that is being experienced. It's
I
actually
understood by
uh,
central loading into R is torsion, but how it, we can call that as twisting while applying
yeah, I get your question. Actually, I am also not very convinced how we can understand this. Mm, but what sir is trying to say here, from what I could get, is that if you take a cross section, uh, so in a way, if you try to visualize, you have this spring of this kind. You are pulling it axially. So what is happening is the ends of the spring will go a bit farther from each other, right? The
it.
So we call it a extension of the spring, but it will
Mm.
also lead to some change in the, I think you can call it the diameter of that coil.
Mm.
And what sir is saying that those members of this the coils in the spring, if you take a cross section, what is actually happening is that those members are just being twisted to some extent, and that twisting is causing this reduction in the diameter of the coil or the extension. So what sir is saying is, due to this twisting in the overall coil, there is some strain that is created, and that strain is coming out as the extension of the whole coil. This is a bit tricky to visualize actually. Krishnakant, you're there?
Yes, sir.
Um, that's how I tried to uh, think how sir might be explaining it. That the extension is caused not due to axial on normal stressing or uniaxial stressing of the coil members. Let's just call it coil members, but actually due to torsion, which is causing some strain, which is coming out as a overall extension of the coil. I'll just try to also Google search it quickly if there is some way to visualize this. So what I can do, Krishnakant, you have any other doubts also?
Just a moment, sir. I will look into it.
Fine. I am also just looking on the web. Maybe I'll share my screen.
Okay. No doubts. Except for this week, it seems.
Okay. Mm.
Mm.
Uh, Krishnakant,
Mm.
you're there. So I could not find any good answers to this. There is one answer. So I'll just show you this one. Yeah. So this is one explanation given. So here you have this kind of a spring which has been loaded axially. You can see.
Mm-hmm.
Hmm. So it has been loaded axially, and it's
Not visible, sir.
the screen is visible. I'll
Huh. Your video alone is visible. Share screen is not there, I think.
Okay, okay. I think it got removed somehow. I thought it was visible. Huh. Now it's visible.
Ah, yes.
Yeah. So this is from a Quora answer. So the explanation given here is if you have this kind of a coil which is given in schematic A
Okay.
and you are loading it axially,
Okay.
then if you try to uncoil this wire, here you have this kind
Mm.
of at the end you have this thing to show that it is loaded in vertical
Mm.
direction,
Mm. Mm.
right?
Mm.
And at the
Mm.
bottom also they have just extended the end, and when you uncoil it, it will be
Mm.
something like this, what is shown in B.
Mm. Mm.
And here it, if you look at this uncoiled one, the axial force is something like this, P acting in vertical direction,
Mm.
and on the other end
Mm.
it is acting in the other direction, opposite direction, and this is the torsional loading, right? Mhm. You can see this is a torsional loading, so this way you can understand that there is torsion being experienced in the wire while the coil is actually loaded. Could you understand?
Um, Almost done.
Fine, fine. Take.
So partially clarified.
At least this is one way of looking at it. Yeah. Yeah, I can't find any good answer.
Okay.
Okay.
So how I understood is basically in the picture showed we are applying force in the center of the axis. So sir is telling it is like torque, right? So torque means the first member, like the coiled member, should get F cross R,
The first
should
member should
experience a force F cross R, which is coiled. Uh,
across R.
there is a spring whose ends are at the center. So if we consider the coiled members force, what it experience, we can tell it is F cross R. From the center, it is radius apart. That's
Okay.
what is called. Like theoretically, it is okay, but I cannot visualize it. How an actual spring is having twisting while uncoiling. I couldn't make it.
I see. Yeah. Okay. I see what you are saying. I'll just again share my screen. So you have it here. So as said that our load that is applied along the central axis and just trying to twist it. So because
Twist,
to resist that
twist means
tensile load.
uncoiling.
Okay, also along with this, it's not pure shear. You also have the axial force, which will be
Okay.
resisting
So is
that one
spring is coiled in 45-degree plane angle? Is anything like that? Will
at
spring be coiled in
45
45
degree.
degrees? Is
Uh,
anything like that?
I don't think so. It depends. The angle will
Okay.
depend. So what sir is saying that if you look at this loading, there will be uh, if you with respect to the central axis, there is a load which is being applied, right? A tensile load on the spring. So
Hmm.
what he is telling
Hmm.
is um, load along the central axis. So this load is trying to twist it with respect to the central axis. So with respect to this axis, you have you have this load P.
Hmm.
So uh, still coming. Yeah, sorry. So actually my pen is not working. Yeah. So you have this P, which is which is applying a torque with respect to the central axis, and because of that, you have a twisting moment on the wire, which is given by MT. So, okay, now I understood. This is what sir is trying to say. And because of that, there will be a torsional moment. Since this P is applied at a distance from the axis, that will cause a torsional moment. And in addition to it, you'll also have some axial force. Hmm. So you got it? Or it's still
Almost done.
partial? And
I'm a
yes,
little bit
yeah.
confused regarding the word twisting in this paragraph.
Yeah, this is difficult to visualize. I think you can also just post a question on the discussion forum if Archita or Ganesh, who is the main TA. He's not the TA, but he's a mentor kind of for us. So he can also
Okay.
maybe give his views. He might have a more deeper understanding on this thing.
Hmm.
So just
Sure. Sure.
post one small question.
Mm. Mm, mm. Sure.
Okay, I think that's all.
Mm.
Anything else?
Done for this week, sir.
Done, no? Okay. So let's look at the assignment quickly. So I'll only cover the portion which is part of the two lectures.
Sir, before getting into the this week's session, I got one question wrong from previous weeks, like for calculating
Okay,
bulk modulus. But I did everything in a right manner as far as
okay,
calculation, I think. So can I get some solving that area? I will tell the answer I got for E also. Um, I got E. Question number 12. Determine the value of bulk modulus in GPA.
hmm, okay,
Okay. E equals to 70.77 GPA.
okay,
Nu is 0.33.
okay. Hmm. US 0.33.
This is 70.77 GPA.
Okay.
Sir, the writings are not
Mm-hmm.
visible.
I'm just looking at the question, trying to understand. I didn't write.
Okay.
So you can calculate epsilon yy as
Uh,
so.
uh,
This is how you do.
Out of four, the three got right.
Okay, so these you could get right? Epsilon v y x. So this
The three got right. Only
okay,
bulk
so this is
modulus.
0.33. This is 70.7.
77.
Okay, 70.77 GPA. Then you got modulus of rigidity as E
G
by
is
2 into 1 plus mu.
I got a
Mm-hmm.
26.6.
How much is it?
26.6.
26.6. Mm-hmm. Okay. Then you have been asked bulk modulus. Then it should be straight
Uh,
away formula, I think. Uh,
but I got wrong.
Assuming isotropic, this relation should hold. So, but okay, what was the value you got?
I got 69.38. But the answer ranging from 179.
179.
170 answer ranges from 179.2 till 198.06.
198. Okay. Okay. Uh, Let me see. The formula is correct, right? According to the lecture. Bulk mode. I'll also go to the lecture and check.
E by 3 of 1 minus 2 mu.
E by 3 into 1 minus 2 mu. And if this value mu is 0.33, then this becomes k equal to E, right? Ah, okay. Then it should, then there might be something wrong.
1.02. 70.77. I'm getting 69.38 only. I don't know how it
Hmm.
got that much, sir.
Okay. 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 So I'll just ask Archita once if there is
I was a little
something.
bit wondering.
Mhm.
Mm-hmm.
I'll just ask Archita if there is something we are missing in this, and
Okay.
you can post it in the forum. Uh,
Okay.
okay. Okay. What you do? Just wait for now. I'll ask Archita, and then she can maybe discuss it
Okay.
tomorrow if there is some way of solving this.
Okay.
Else, you can put it on the forum.
Okay.
Yeah.
Mm.
Tomorrow, you can just ask her once about this.
Mm.
Yeah. Okay. So should we go to assignment 7?
Mm. Okay, sir.
Uh,
Twisting.
yeah, twisting.
Right.
Identify the zero components.
Sir, a little bit zoom. So options are not properly visible. Ah, okay. Zero components. So twisting. Is in Z, right? Except gamma Z, I think all the stuff will be zero.
Okay, so all of the others, yeah, you are
Right?
right. Only gamma z theta will be non-zero. And what is the assumption due to which you have this? Can you tell?
What is assumption?
Hmm.
Means
I'm just asking, maybe if you can answer.
we made only two assumptions. The plane should be always circular and deformation will be always straight lines, not a curvy one. Like thought like it is an RZ plane only that twisting is happening. So if we go to animation and apply RZ coordinates there, the twisting also will be linear in RZ
Um,
plane alone. So
can
the
you
rest of the
repeat
planes
once?
will not suffer any
Actually, your voice was breaking. Can you repeat once what your
twisting.
explanation was? Your
Is
voice was breaking.
the is it okay now?
It's better.
Yeah, the twisting is happening only in RZ plane. So if we
Hmm.
substitute the coordinates to the derivation where we derived phi, so we will get in terms of RZ. Uh, there we got in z theta because we used theta z coordinates there. If we substitute RZ and make the derivation, except phi RZ, everything will become zero. And
Except
also,
by. Okay.
since the deformation happening is a straight line, so we cannot say it is not it belongs to other coordinates also.
Hmm. Okay. No, I did not get. Why should on RZ you have strain? You're saying you'll have strain on RZ if you use the RZ coordinate system.
Yes.
But there should not be any strain, because if it is like this, let's say you took a small element here, maybe like this, right? Yeah. What you or let's say it was something like this. Let's this small element.
Mm.
Then what you'll see is that this got sheared in this direction, right?
Mm.
Along theta it is getting sheared, and this plane, mm,
Along theta.
yeah. So this is
Along.
the, let's say this is the theta direction here. This is R, and towards the top it is Z, like vertical, right? R is
Okay.
always radially outwards, right?
Mm.
So this is the plane on which shearing is happening, which is the Z theta plane.
Mm.
If uh, if I magnify it, it looks something like this. So you
Mm.
have
Mm.
you
Mm.
have kind of
Yes, sir. That
you
is.
can understand it as something like this,
Uh,
right?
mm.
This is your Z theta plane.
Okay.
So that's why I was saying that only on this plane you will, only in the theta direction you have shearing, which uh, sorry, this is not Z theta plane. Yeah, it's Z theta plane, yeah. So only on the Z theta plane you will be having shearing.
I thought like here it is there in a RZ plane. Clockwise movement is being applied. Clockwise. Anti-clockwise movement is being applied. So I thought RZ plane will experience the shear.
Our Z plane will experience the shear. Mm,
Oh,
On the RZ plane you have not really. It the um,
I
shear
think I
stress
have to check the
is
coordinates.
uh, oh, let's say here you have Z, right? Let's say this is Z, this is
Mm,
theta, this is
mm,
R, right?
mm. The
So
sharing is happening in Z theta.
shearing is happening in this direction.
Mm.
Hmm. And mm, yeah, so shearing is happening like this. Hmm. I'm also trying to think, like, make it clear what is going on. Uh, hmm. Yeah, I also have some confusion. I realized. Let's just go here.
You have to.
Z.
So in the question, so here if we see the coordinates,
Hmm.
the
Yeah.
torsion is being applied in the plane of z theta.
Sorry. Wait. Uh-huh.
In notes, if we see the torsion is being applied in the plane of z theta, whereas here it is being applied. Okay,
No,
okay.
no. The torsion is up. Twisting movement is same in both. Just here.
Direction.
Hmm. Hmm. Sir is also explaining in a similar manner. You can look at it like it's visible.
Hmm.
So this is the
The
theta z
picture is
plane,
visible.
right? Uh, this is the coordinate system.
Hmm.
This one,
Hmm.
and the theta z plane is the e naught f1 h1 g1 one. Like it's here also.
Like how we
Mm.
understood is other than z theta plane, if we
Hmm.
consider z theta alone as a 2D plane, other than that z theta plane, whichever plane we take, we cannot see the variation.
We cannot see the twisting in
We
the
will see only dots or only line, single line. So we can abruptly tell that this is where the deformation is happening.
hmm. Yeah, yeah. So yeah, that way you can understand it. So so that makes sense. No, now you have some. I also could understand that way we can see on which plane you are having this shear kind of straining taking place. That I'll switch on the camera.
One small help for me. Uh, can you make some lines like it's shared so it will be a bit easier for to visualize? In
Yeah.
there in
So here, if we just
assignment.
try to magnify it, it will be something like this. This was the original one, and it has shear. This is z. Sorry, this is
Theta.
theta axis. This is the z axis, and because this is with respect to, so tau is in this direction, shear stress. So because this is the plane where you have the shearing, that's why it is being said that it is z theta plane on which the shear stress is acting.
So in that assignment question, can you make some
Hmm.
lines like it got shared?
Similar to this, no? Hmm.
Anti-clockwise. Yes.
So maybe another way to see this is if we
Sir, actually, other than RZ plane, the deformation will not be visible from any other plane, right?
other than the RZ plane.
Deformation will not be visible from any other plane. So if we draw a line also, we will be getting to know that now. Like
Hmm.
taking the origin as a dotted dashed line, so we can give some sheared lines from the origin, like
From
separating the
origin,
cylinder into two by drawing a dashed line.
separating into two, you are saying.
Because both are different now. So this side is anti-clockwise and that side is
Hmm.
anti-clockwise. We'll be getting
Okay.
different lines. And from that line to the right side, it should be bottom wise
Hmm.
lines.
So if you have something like this, what are you trying to say in this?
We from lines will be like from the origin to the fourth quadrant.
Origin to the fourth quadrant.
fourth quadrant.
No,
The cylinder will, the straight lines will shear like that if we apply
uh,
anti-clockwise moment.
no, no, I could not.
Because you're twisting anti-clockwise, it will, like straight lines will make
Just give
a
me a minute,
like
huh?
this.
I got a call. I got a call, huh? Give me a minute. Yes, Krishna Kanti.
Yes, so before applying torsion, it will be straight lines. So
It
like
will
how sir
be
usually puts straight lines on that soft materials. So like that, if we try to understand, it will be straight lines before torsion, and
okay.
after anti-clockwise movement,
Hmm.
those lines will get downwards. Like how the uh, line we can draw from origin to fourth quadrant, like this.
Okay, I got it what you're saying. Actually, it's better to just look at the way sir had told, because here you are looking at basically changing the direction of the shaft, right? And
Mm,
making it
mm, mm,
horizontal instead of vertical. So it's the
mm.
same thing only. Uh, because better to like understand from this thing only, because here sir has uh, shown the strain also. So you can
But
relate this
sir,
to
the
that also.
coordinates had been changed in the question.
No, coordinates have been changed.
The
I
plane,
don't think so.
yes, sir. The planes have changed. In place of a
No,
theta, they have put a z. In place of
no. It's not changed. It's exactly the same, because see, z will always be along the axis. As you see here, z is along the axis.
okay,
R is
understood,
radially
understood, understood,
outwards. Theta is
understood.
along the circumference.
Mm,
So
mm,
this
mm,
is
mm,
exactly the same. If you have understood here what is
mm,
happening,
mm, mm.
then is the same thing happening there. So actually
Okay.
another thing, no, that why I also got confused was because sir told, right, if you convert this to Cartesian system x, y, and z, then you will have a tau
Mm,
both in let's say both in the
Excellent.
xz and the yz direction. So you have a tau here also and here also. In
Mm,
this you will have it 0,
mm,
but
mm,
in xy it will be 0, but xz and yz will have a value. But if you see in
mm,
polar system, then only this one plane is there which is getting shear.
mm.
Maybe here you can see it's this one here, or in the slides it's this one. Um,
Easy data.
okay, it got removed. Yeah, z theta 1. That is where the parallelogram was forming, right? Due to the staining.
Mm,
Yeah. That's why z theta will be the plane where you have the shear stress. You understood now?
Hmm.
Like it's more clear, no?
Got confused with coordinates.
I think that I couldn't catch that you were looking at the this coordinate system. So both of them have the same notations. They are not different.
Hmm.
This is the convention which is followed for all polar coordinates.
Okay.
Axis will always be z.
Hmm.
So okay, next question.
Identify the correct statements and how shaft can transmit more torque. Yes, than a solid shaft at same weight. Yes, one is correct. The assumption of plane.
Mhm. One is correct. Okay.
The assumption of plane cross section remaining plane before and after loading holds true for shafts of any cross section. Two is wrong. Uh, for a shaft transmitting torque, the maximum shear stress occurs at circumference of the shaft. Shear stress. Okay. Mm, equals to 16 MTP. I didn't. The torque is maximum. So therefore the maximum. Yes, true.
At the circumference. Okay.
The hollow shaft of the same material and the same outer diameter. Oh, a solid shaft can transmit more. Oh, uh, sir. Actually, fourth question is a little bit confusing.
Okay.
If the hollow shaft with the same material means the outer diameter will vary for the hollow shaft comparatively because the center became hollow. To use that material, we will get a higher dia denote, outer dia. For the same
Uh,
material and the diameter same.
hmm. Can you
If I think either of the so for the hollow shaft, if we consider the same material criteria, because the material
Yeah.
had been taken from inside, the
Hmm.
diameter, outer dia of the hollow shaft will be always greater compared to the solid for same material.
Okay. Yeah. Okay.
So because like you can understand, like inner material will be used on outer side.
Uh,
So the D naught will be always higher for a hollow shaft for the same
no,
material, but
no.
they are
Inner
telling that
material in this option is not saying the inner materialing is being used outside.
like kind of understandings. So if we remove material outside, we have to use that material now because they had said the same amount of material. So we can understand like it will be used on outer side, like, just for understanding purpose.
Okay.
Like for same material means same amount of material is being used for same shaft, these two shafts. So the diameter for the hollow shaft should be higher,
No, no.
should
That's
be higher.
just try to read the option slowly.
The hollow shaft of the same material. Okay. Oh my God. I was thinking a little bit wrong. So, the hollow shaft of the same material and the same outer dia as a solid shaft can transmit more torque than solid shaft. No, it cannot.
Yeah,
I
because
think
yeah,
I is no.
no, yeah. You know the reason for this?
Uh, one minute, sir. So solid shaft can transmit more torque. Huh? MT equals to uh, tau into IP by R. The IP will vary. IP for the hollow shaft for in diameter will be lesser compared to solid shaft.
Yeah. Yes, yes.
So
Hmm.
by seeing the same material, what I thought is they had been using the same amount of material.
Yeah, I got your confusion, but that's not the case. Yeah. And a simple way to understand this is that if you are removing some material, then um, the kind of the movement, twisting movement, which was being accommodated by that particular amount of material in the inner diameter, that is not there anymore, right? So the outer part will have to accommodate more of that movement. Uh, or you can say that all the stresses will get restricted between the inner and outer diameters instead of the whole from the center to the outer diameter. Was I clear?
Mm.
Hello.
Yes, sir, you are clear.
So basically, it's the same thing as you said. Moment of inertia is higher uh, for the solid shaft compared to
Sorry.
hollow shaft. Yeah, same thing only. Then yeah, this is the last question. Just see how you will approach this.
Okay. Uniform solid brass shaft is applied with the torque T. The free end strain gauge is placed at point P. This point P. Okay. On the shaft surface at the angle shown measures 325 micro strain. Okay. 45 degree plus 325 micro strain. Okay. When the torque is applied, answer the following questions based on the data. Okay, the magnitude of maximum shear stress in MP experienced by shaft. Maximum shear stress. This first question is question 4 is directly application of formula like tau equals to 16 mt divided by pi dq. Uh, the magnitude of applied torque in Newton per meter, but we won't get maximum shear stress now because we don't have torque. Tau equals to 16 mt by pi dq, but we don't have mt.
Mm.
We have mt, I think. Uh, just just for clarification,
Mm.
this is a pure shear. So at
Yeah.
45-degree, it should be sigma x minus sigma equals to minus sigma y. So if it is showing plus 325, it should be sigma x, it's in positive direction. So that should be the pure shear also, value also, right?
Maximum.
So in a Mohr
Actually,
circle for pure shear stress, if we draw,
hmm.
we'll be getting one side it should be 325, another side it should be minus 325.
Yeah,
So we
yeah.
can tell tau also should be,
Tau, the
so we can
shear
tell
strain is
directly it should
also
be
325.
325.
The shear strain will also be
And with that
325.
we can
Like
calculate torque.
with that, you can
Shear strain.
calculate torque.
Oh,
Yes.
oh, 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 oh. Shit. It is shear
Uh,
strain. Huh? Okay. So
that
we
is
have
the
to
shear
multiply
strain
with
that you
E
have
and
to
then
convert to
we
the
can.
maximum shear stress.
Multiplying by E and we will be getting shear
Uh,
stress.
so
With
you
that shear stress, we can calculate
yeah, tau
E
equal to
equal
G into
there is empty
mu,
phi
and G you
mu.
can
Okay.
calculate, right?
Mm. Uh, gi-
Equal to 1 plus mu.
mm.
Hmm.
And for calculating T, it is like MT equals to tau IP by R.
Mt equal to tau
Tau IP
IP
by R.
by R.
We'll be getting maximum moment or maximum torque if we use maximum shear stress. And the magnitude of maximum angle of twist in degrees undergone by shaft. So generally phi equals to MTL divided by uh,
Hmm.
GIP, and the whole should be multiplied by 185 pi.
Okay. Actually, I didn't get your answer for question 5. So which formula is this one which you used? One we have is this, right? That GIP into phi by
G,
Z, GIP by L equal
I
to
don't know.
MT by phi, right?
Ah, GI, I didn't get you, sir.
Like this one that you used, where did this come from? This formula?
Which formula, sir?
GI. You told this one, right? The one in arrow.
Yes,
You,
yes, yes. This is from this equation, torsion equation. So we have something torsion equation stating that MT by IP equals to tau by R equals to G5 by E. G5 by E, yeah.
uh,
G5 by L.
huh,
Sir told this equation is very important to remember something.
okay, yeah, yeah, yeah. Hmm. So, okay, maybe I didn't notice that. So, MT here is equal to tau into IP, G5 by L. Okay.
MT by IP equals to tau by R equal to
Okay.
G uh, 5 by L.
Makes sense. So this is just another form of this other equation because
Hmm, 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 hmm.
phi by L is constant
Hmm.
and so since tau is equal to G phi by L, tau is equal to G into d phi by dz, which can be written
Hmm.
as G into phi by
Bye bye.
L. Yeah, yeah.
Hmm.
Mm-hmm. So okay. So using that you can calculate T,
Hmm.
the applied moment. And now the last question is maximum angle of twist. What answer did you give for this?
It's, like the same only. So phi equals to TL divided by IP into G.
Tau L divided by IP into G, right? Just same equation only. Here
Hmm.
you are using this thing that G into phi by L equal to tau, the shear
Hmm.
stress. right? Okay. So I think with this we are done with the assignment. Yeah. Okay, Krishnagant. Uh,
Sir.
Let us end this session now. It was a good discussion, I think.
Sir.
For me also, it became more concrete, some of the concepts, and looking at it again. So let's finish this session. Thank you for attending.
Sir.
And I let ask Archita about that question which you had told from previous assignment.
Hmm. So, likewise, I got three questions wrong. Like that, one question is there in temperature variation also. So the two got wrong. So I don't know
Okay.
what mistake I did. So I checked it twice also. For my eyes, I
Uh,
didn't got any mistakes. So I have to get
okay.
clarification.
Okay, let's see. Mhm.
So,
Oh, thank you for joining.
thank you, sir.
Bye.
Bye.